Basically, the topic of this short 2 days program is regarding machine learning. So machine learning is nowadays pretty hot topic. Everybody is jumping into it. In our IIT also, a lot of people are now working in ML related areas, not exactly ML, but something which uses ML or AI in their research, and so do we also do that. I primarily work in financial mathematics. Financial mathematics is more related to your stock market and money making. तो जिसको पैसा कमाना होता है वो फाइनेंशियल मैथ्स पढ़ लेता है और हमारे many of our BTech students are enrolled in this financial mathematics courses in recent years. Reason is कि बहुत सारी investment banking companies आती हैं जो हमारे बच्चों को hire करती हैं तो finance में everything is regarding the data. So stock market is all about data. So that is how we come in learning tools in our research purposes or for our research problems. So all your like cyber security, network security, etc., all that is a part of your financial maths. So we do work in those areas, but right now I'm not into that because I know that you people are basically undergrad students. So teaching you something from our research may not be very fascinating and may not be appealing to you right now at your age. So I have restricted myself to a very, very simple thing which you people, all of you are studying but perhaps not knowing it. So most of you might be from maths and computer science background or maybe from some other science background, but all of you study basic maths. And in basic maths you all study something which a subject called linear algebra. And in linear algebra you all study something which you call as eigenvalues and eigenvector of a matrix. So maybe if you are from first year or second year you might not have done those things, but sooner or later you might be doing all this stuff. That what is matrix, what is eigenvalue, what is eigenvector, etc., etc. But the way we teach, because I am a product of Delhi University, I know how we teach, right? I was a part of that. I was a faculty in Acharya Narendra College. So the way we used to teach, because we have deadlines, we have syllabus, we have to complete it, and we have a very limited time span in which we have to explain too many things to the students. Specifically, most of the students are interested in exam perspective, that whether this topic is going to come in exam, whether this is not going to come in exam. If something is not going to come in exam and it is not a part of a syllabus, don't teach us. It's a very standard way of doing the things. So therefore, when we used to teach eigenvalue, eigenvector to our first year undergrad students or second year undergrad students at that time point, maybe 10 or 20 years back. So the way we used to teach it is like this, that given a square matrix, we define what do you mean by eigenvalue, eigenvector, we tell them the method to compute those values and then do a lot of question on 3x3 or 4x4 matrix, and that's all. And maybe we do a little bit of properties of eigenvalue, eigenvectors, and then we just leave it there itself. We don't tell them that why we are studying all this, why it is important. And because sir has been using image processing, so basically linear algebra is very, very pivotal for all machine learning. If someone want to make a career or someone want to pursue higher study in ML, you have to have a very sound knowledge of machine learning and statistics. These are the two things which are very integrated into all the AI science, data science, you name it and you have it. So students of maths specifically, whenever you have a chance to study LA or statistics, please remember this, that it is a foundation for all the ML data science courses. And in fact, all engineers also have to study these two topics, probability statistics and linear algebra. If you don't have that, then it will be a lost world for you. But unfortunate thing is that when we teach these things, we don't connect them to ML or to data science or to AI. So my idea basically is not to give you too much of technicality, although my slide may be more technical, but I would like to talk more. So now think of a situation where you have a data. This may be a, so basically a data for me is a matrix. It's as simple as that. So matrix means that first of all you decide that what is the problem that you wanted to address to. For example, if I am interested in students' data, as Principal Sir was right now talking about that how many students are there in 4th year BSc. That is a question which he was trying to figure out. So this means he wanted data basically as how many students are officially now registered in 4th year BSc program in this college. Now suppose if I just look at that, so now you have 1 year, 2 year, 3 year, 4 year, and I just want to see that how you are performing. Suppose if you continue till 4th year, how you are performing in these 4 years vis-a-vis your academics, vis-a-vis your extracurricular, vis-a-vis your sports, or some other kind of activities, including this, tolerating us sitting here. So if we try to collect that data, to me it would be if there are 564 students, as the number was told to the principal sir. So 564 students and 4 year data, because they must be here from 1st year till 4th year. So this will be a matrix for me, which is 564 cross 4 matrix. 4 is the number of column which represent your years. So this 4, which is represented by column, is something which we call as features, because, or something which we call as characteristics or attributes, where we want to analyze these features. We want to analyze our data based on these set of 4 questions. It could be like this, that at the end of every year, suppose if somebody asks you to give a feedback of your course, or suppose in this room itself, at the end of every day suppose if you have 4 lectures, so total 8 lectures. So at the end of 2 days, suppose if the organizer asks you to fill a feedback form. So how many questions will be there? That is up to the organizer. They can write some questions, and then they will ask you to answer those questions about, these 8 lectures. So this is a kind of data that you are working with. Now suppose if the organizer framed 10 questions. So that means 10 will be the attribute, the number of features that we have. And how many students fill that, then that means 25 rows. So for me, our data is a matrix which will now be 25 cross 10 matrix. Right, where 10 will be the number of questions that have been asked. And I want to analyze this data based on the feedback that on average, what is my feedback, for example? Is it good? Is it bad? Is it average? Is there a scope of improvement, and so on and so forth. So whenever you are working with data, as a statistics person or as a person from data science, we always arrange columns as features or attributes or properties or characterizations or questions, or it may be a survey and these may be questions as we have been telling you, and the responses to those questions. The responses to those features are arranged in row. So therefore this X, which is this sigma which I write, this is, so now if I have an n cross p matrix, for example, so n is the number of rows, p is the number of columns. So now the first question that I may ask is, many a times, in fact in our own system, IIT system also, whenever we have this feedback mechanism, or you go to bank and you are applying for a loan, for example, they will ask you to fill some form and there are P questions. Many a time you find that most of the questions are redundant actually. They are asking you the same information but in a different sense. For example, if they ask you, what is your salary, right? So they will give you some range. So suppose if I feel that my monthly salary is somewhere between 1 lakh and 1.5 lakh, it means that I am already in the upper middle class as per the economic standards of India. So then asking that whether you owe a television at your home, this seems to be a very redundant question, because Somebody who is in upper middle class will be well off in the sense that he or she will be possessing mobile. That is something which we all expect, right? Or maybe a small car, if not the luxurious car, maybe some small television, if not the big television. So therefore, asking the similar question again and again doesn't give you any extra information. If I am asking you to fill a feedback for a teacher, for example, faculty, so there may be one question whether the teacher has taken a class in time. And the second question is whether the faculty was, regular in the classes. Both the questions have the same answer, but I'm repeatedly asking you the similar questions regarding the teacher. So basically, when we have these P questions or P features, many of these features may be not independent of each other. They may have some kind of dependency structure between them, or you can say that many of the questions are redundant. Now, one way could be, which all of us can do is, okay, I have say 50 features. So find out the features which are redundant or useless, or they don't provide me any substantial new information. One way could be brute force. Just identify which of the questions are repeating and asking the same information and just remove them. So instead of 50 questions, I may boil down myself to 30 questions or 35 questions. That is the brute force thing. But that may means that I'm not sure that the questions which are deleted, say 15 questions or 20 questions which you might have deleted, whether they do contain some vital information statistically or data-wise, and somehow when I'm applying the brute force, I'm just keeping 35 questions and just removing the 15 questions in the dustbin. But this dustbin part may be vital. For example, suppose if I gave you that some vegetable to chop off, or let's say some watermelon, right? And I just want to eat it. So you just have to peel off the upper part, green part, and just eat the red part. Now it depends on you that how you are peeling it. So as a mother or as a housemaker, typically we do it in such a manner that most of the red part remains, and in fact many of the ingredients, because we are not going to throw everything in the dustbin. We will keep in mind that too much waste should not be there. Everything should be eaten as much as I can. But suppose as a person like you, youngsters, if I ask you to peel the watermelon, you will just take a knife, cut it this way, and just eat the red part and throw everything in the dustbin. And when you see the garbage which you have thrown, much, right? So that you could have eaten. So my question is, when I'm throwing something out, am I sure and confident that I am not losing too much of information? I'm just retaining what I want to read, and I'm just throwing something which is minimum information. So in a large data set, finding out this redundancy requires some kind of meaningful mathematics. It cannot be that one day somebody will come and chop off the data. You have to think about it, that what to keep and what not to keep. So this is what we call as data reduction schemes in machine learning or data science. That what are the methods by which if I'm working with a very large data set where my P may be very, very big number, 500, 1,000, maybe more than that also. Sometimes, for example, in biological data, which sir might be telling you later on, you find almost like genome sequences are there. So you might find that your P is running in 30 lakh, right? So therefore, if I'm keeping this much of big data and working with such big data, maybe every information I don't want to keep myself. So I am looking for some data reduction technique. One of the oldest technique for data reduction is principal component analysis. And the entire foundation of this technique lies in linear algebra. Absolute linear algebra. Any student of maths who has done eigenvalue, eigenvector, they will easily know what is PCA standing for and what exactly it is doing. So how do we do it? And this is one of the oldest technique. Nowadays, little bit outdated also. And I will tell you why it is outdated and what new techniques are there. But perhaps this is the oldest and this is the easiest one with which all of you can connect, because all of you are doing linear algebra in your undergrad courses and statistics, of course. So what we just do is, I am not going to apply brute force to chop off the data or to reduce the data. I am going to do a little more mathematics. So first of all, I have n cross p matrix with me, which is my data matrix. And p is the number of features, right? Then what I just do is, given this data matrix, I am going to find out variance covariance matrix out of it. Now, how do we find out that? What do we understand by variance covariance first of all? So variance basically means, or variance or covariance basically means that you are trying to capture linear dependency in the data column. Linear dependency. You know what is linear independence and linear dependence. So I am not talking of anything non-linear. The non-linearity could be very complex, and that has to be modeled separately. We are trying to find out, can I write any particular column as a linear combination of the other columns? Is it possible? So can I write my first column as a linear combination of some subsequent columns? Or second column, or third column, or fourth column, any ith column. So this linear dependency, if I want to figure out, I have to work with something which we call as variance covariance. And this also captures what you call as little bit instability in your data. So for example, if I am asking you a question, is the teacher coming in the class regularly? And suppose there are 30 responses coming from it. Most of you, if the teacher is actually regular, most of you will write yes. So suppose yes means 5 points. So most of you will give answer 4 or 5. That means the teacher is pretty much regular. But some of you who yourself are not actually attending the class, right? You may not be knowing whether because you yourself are not coming to the class. So therefore, many of you may say, I do not know. No opinion. Or you may say, the teacher is not coming regularly to the class because you just want to save your skin also. So therefore, you will give the point as 0, 1 or 2 also. Right? It depends how you treat it. It is your perspective, your survey. Now when I am giving you this, so what I found is that on average, the teacher has scored, let's say, 4 marks on average. But there are deviation away from it because the students have given marks like 0 also. The student has given marks like 1 also. So there are positive and negative deviation around the average position. I want to capture this deviation. And as a person of statistics, you know the best way of capturing the deviation from the average position is your variance. Standard deviation, square of standard deviation. This you might have done in your 12th class also. So suppose if on everybody in this classroom say on average, everything was okay. So the answer is, average answer is okay, everything is going fine. But there may be 2 or 3 or 4 of us who say it is all very boring. We are just forcefully sitting here. I'm not even interested. But what to do? I have no other choice. So that means you're deviating from the average position. So if I want to capture this deviation mathematically, I have to work with standard deviation or variance. And if you are capturing 2 data series, this is variance is in 1 data series. How much we are deviating from average, that is in 1 data series. But suppose if I have 2 columns, or if I have multiple columns, second column, third column, fourth column also, and if I want to capture their dependency, answer of first question, is it dependent on answer of the second question? Or answer of third question, is it somewhere correlated to the answer of 10th question? So in that case, I will find out something called covariance. So I will find out the correlation between these 2 data series, or some kind of variance between these 2 data series. And that is how we are going to construct this matrix, which I have denoted by sigma here. So this will be a P cross P matrix. for every column, first column it is something like very similar to your partial derivatives. So if I give you p number of variables and if I ask you to differentiate it, so then in that case, if I look at first order partial derivative, how many partial derivative? P. But suppose if I am looking for second order partial derivative, so 1 with 1, 1 with 2, 1 with 3, 1 with 4, 1 with P. Then 2 with 1, 2 with 2, and so you are going to do 2 times. 2 variable you take and look for the second order partial derivative. So this variance covariance is something like second order differentiability, something of that kind, very similar to that. It is second order quantiles which you are capturing, some kind of deviation from first differentials are like your mean, average. That is your first statistics. Standard deviation is second statistics. So it is like second order partial derivative. So if I give you p number of variable and if I ask you find out the second order partial derivative, the total number of derivative will be p square. And if you arrange them, it will be a p by p matrix. So that's exactly your sigma matrices. Now what I just do is, because this is basically capturing some kind of volatility, some kind of deviation. And then I remember something which Virat Kohli once said. He said, if I score century and everybody clap and start praising me, it does not give me anything actually. But if I'm not performing well and people start criticizing me, then it gives me something to think. So what I'm trying to say is, people who are on average, people who will say, yes sir, everything is okay, yes, nice, they are not vital for the system. They will not give me any nice information. People who are critical, people who are deviating from this yes boss kind of attitude, people who say no, this was mistake, this should not have been done, they are the ones who are vital. So this actually captures that, right? So this is not important. So this I have already told you. So what we are going to do is, we are going to find out how many features I have to keep and how many features I can delete. So for that, so all this, we are going to find something which we call as principal component. So what we will do is, there are two ways of doing it. As I told you, one is purely from linear algebra perspective and another is little bit of statistical perspective. So what we first try and do it, we first find out the first principal component. That means which feature or a combination of feature I am supposed to keep. So what we do is, we find out the eigenvalue and eigenvectors of this matrix sigma, which is your variance covariance matrix. So it will have p number of eigenvalues and p eigenvectors correspondingly. So what we just do is, we keep, so if I have p number of eigenvalues with me, I will try and keep those ones which are top bigger ones. That means I will arrange the eigenvalues in the ascending or descending order, whichever order you want to arrange it, and just keep the top one. How many you want to keep, I will just let you know, but out of these p, we are just going to keep the first k of them. So I am not going to keep everything. We will just keep few of them and the corresponding eigenvector also. The corresponding eigenvector to those which we are keeping. Those eigenvectors will give me or will help me to construct what we call as principal component. So this is what we have done here. So first thing is, what we do is, the first principal component is denoted by y1 here, and it depends on a vector a1 where x is a data matrix which is given me. So I will first find out a vector a1 in such a manner that this variance, that means this quadratic form, is maximized. So this is what we are trying to do.
रोटेट हो गया वो ऊपर से और फुल स्क्रीन कर दे फुल
transpose sigma a1 which is your quadratic is maximized. The problem is that this A1 transpose sigma A1 could be a very large positive number, and it can go to infinity because A1 is not in my control, it could be any vector. So in that case, what we just do is, because this problem becomes unbounded, but at the same time, length of A1 should be maximum 1. That means we try and find out all those unit vector A1. So we create a unit circle. So unit circle is, or unit circle in p dimension, or you can call it as unit sphere in p dimension. So we are trying to find out those A such that length of A should be 1 and this should be maximum. So this is a classical optimization problem. And what we just do is, so we try and solve this problem. But this turns out to be a very nice problem to solve, and it can be easily solved. It's not very difficult actually, because it has some nice geometrical properties. So we find out A1 from here. What is the solution of this problem? Whatever solution turns out to be, whatever that A1 star is, that we take, so we find, using that A1 star, we find out Y1. So suppose my A1 star is 2, 3, 5. So we find out Y1 as 2x1 plus 3x2 plus 5x3 as my first principal component. Principal component, as I told you, is basically either the feature itself or it could be some linear combination of that feature. So that gives me the first principal component. Then in order to find out the second principal component, we have to find out the second vector A2, and we will try and solve this problem then. So I want to find out A2, which is again a unit vector, and it should maximize the variance. So again it is a similar problem as that of A1, except that A1 is now replaced by A2, and A2 is also a unit vector. But I have an extra condition, and that is that these vectors should be orthogonal to A1 with respect to a sigma matrix. That means that the covariance of A2 and A1 with respect to sigma matrix should be 0. They should be independent of each other. So because of that, we have one extra condition coming in here, which is A2 transpose sigma A1 equal to 0. So we try and solve, and this is again a nice optimization problem which can be solved statistically or otherwise also. It is a convex problem, so it does have a solution. So we find out A2 star from here. Whatever that A2 star is, whatever is the solution of this problem, we will find it out that. And then we are going to, once this A2 is with us, we are going to construct a second principal component Y2, which will be A2 transpose X. That means, suppose if my A2 star is say 1, 0, minus 1, then in that case my second principal component will be x1 plus 0 x2 minus x3. So that basically means x1 minus x3 only. So in this way you can keep on constructing the P principal component, because I have P features, so I am going to take P linear combinations. And out of that, this is what I have been trying to say, that we find out the eigenvalues and eigenvectors. And then we will keep only those out of these P principal component that we have calculated. We are going to keep only those which are top one. Now how do I decide which are top one or not? So what we just do is, this lambda, which is your eigenvalue, contain all vital information. So what I just do is, I sum, first I create this sum that, suppose if I take the sum of lambda 1 plus lambda 2 plus lambda k, where k will be right now. This k could be 1, 5, I don't know. But suppose if I take some k, at which I will just add these lambdas, and I sum total all the lambdas. So what I do is, I sum total all the lambdas, and I sum total the first k lambdas. where I do not know what is k, and I take this ratio. So I take the ratio of first k eigenvalues, sum of them, divided by sum total of all the eigenvalues. And then I will choose k in such a manner that this ratio is pretty high. So it means k is the smallest positive integer for which the ratio, which is sum of first lambda k's, the first k lambdas divided by sum total of all the lambdas, that ratio becomes very high, almost nearly 100%, if not exactly 100%. Now it is up to you how much threshold you want. So suppose if I am okay with 95% or 90%, then I will stop at that value of k where this ratio becomes 90% or 0.9. Right? The moment it becomes 0.9, what is that minimum k at which it becomes 0.9? What is that first value of k? That as my number of principal component that I am going. So suppose initially I have started with 500 features. I calculated 500 principal component because there will be 500 eigenvalues. I have 500 eigenvectors with them. These vectors will be orthonormal. Orthonormal means that they will be orthogonal and unit vectors. And what I just do is, out of 500, if I found that at 95% my k turns out to be 200 or 220, then I am going to keep only first 220 principal component with me. The rest I can delete. So this means I am going to keep only the first 220 linear combination. So that means initially my data matrix, which is n cross 500, where n is the number of observation, and I am keeping just 220 linear combination of that data with me. So my next transform data will be 500 n cross 220. N will be the same but 220. So the number of column has drastically reduced. Now instead of working with 500 data sets or 500 features, you have to work with 220 features only. And these eigenvectors help you to construct those principal components. So basically, if you have E1, E2, E3 and E220 are the first 220 eigenvectors corresponding to lambda 1, lambda 2, lambda 220, then in that case my principal components will be y1, y2, y220, and that will be basically sigma times E1, sigma times E2, where sigma was my initial variance covariance matrix. So in this case, I can find out what is the data matrix that I am supposed to work with, right? And that helped me to reduce the data. So instead of working with big data, you are preserving all the vital information. And what is vital here? It is the variance. So I am preserving the maximum variance or maximum deviation. That means I am basically focusing on the voices of the students or voices of in those surveys which are critical voices. I am keeping all of them with me. I am not discarding them, but I am just taking a little bit of linear transform form of that data. So this is one way of data reduction. But as I told you, this is not the only way. There are many other ways which are now more recent, of course. The major limitation of this method is that everything is very rosy here, in the sense that everything is linear dependence. Every data which we are taking, whether we are working with variance covariance, whether we are working with eigenvalue, eigenvector, we are always assuming that my data has linear dependency structure. So it does not talk about non-linear dependency. I mean to say that if my data first column and second column or third column, suppose if I have only 3 columns, and if I say that first column is alpha times second column plus beta times third column, that is linear structures. But it does not say anything about non-linearity. It may be that if I plot the graph of x1 and x2 axis or x1 and x2 data, it may be parabolic. But I am not taking that. I am always taking straight lines. All my principal components are linear combination only. So that means they are basically straight line vectors. So I am trying to find out the variability. I am keeping and preserving the variabilities in the data which are variability along those straight lines. But suppose if I have parabolic structures or elliptical structure or some other kind of geometrical structure, maybe very complex geometrical structure, then PCA does not capture that. That is a major drawback with PCA, the standard PCA. So what people have done and what machine learning people have been doing is, anything which is not workable linearly, they try to create a kernel trick in that, and then they try and create a geometry which ultimately boils down to linearity. So initially it is not linear, but after doing some little bit of juggling through kernel mappings or kernel function, they can create some kind of linearities. So how do they do it? And this is very well known kernel tricks in all machine learning things. You name it and they will be having it. So basically the idea comes like this. Suppose if I do not have a very nice relationship with, let's say, my parents or with something, my friends. So it's not a very linear kind of, things are little complex. Things are very difficult to explain that we are good friends, but if somebody asks me to explain it, it becomes very difficult. Because it is not that both of us are loving the same things, both of us are hating the same thing. So it is not linear, but a little bit non-linearity. But if I try to capture that non-linearity, either I should have some mechanism of capturing the non-linear relationship between me and my friend. Another way could be that some third person jumps in and he start creating lot of misunderstanding between two of us. So basically he is giving some heated arguments. He will say n number of things to me about that fellow, then he will go to that, say n number of things about me to that second, my friend. So somewhere, he is like a person who is adding some kind of pinch of salt in between the relationship. Or you can say he is boiling the water. The water which is more or less stable between two of us, he's just putting some heat and boiling it. And it becomes vapors. We both will get so angry with this third person that, why he's interfering in our relationship. So for example, if I have a fight with my father for that matter, so it is between me and my father. If some third person jumps in, even you will not like it. That why this third person is, abusing my father. He is my father. I have a right to abuse him. But he does not have a right to abuse him. So basically, what you just do, this kernel is doing is, it is acting as a third person. What this kernel is doing is, it is just boiling the entire data in some sense. So it is throwing this data into high dimension. Something which was in 2 dimension or 3 dimension or 10 dimension or 500 dimension, it starts adding more and more ingredient to this data in such a manner that it boils down, it becomes a vaporous state, and then it spread out in high dimension. So something which is very non-linear here, something which was parabola in, let's say, 3 dimension or 4 dimension, or very entangled, something which we could not explain. And that is why the problem was, because I don't have a linear geometry. So when you boil something and it becomes vapor, it becomes gaseous state, then in the vapor they spread out, the data spread out like anything. And then it becomes very easy for me to, because I have opened this entanglement. This is now gone. This has broken like this and everything is in spreading out. So now it is very easy for me to create a linear geometry. So that is what exactly kernel does for you. In fact, that is why it is called kernel. So basically, it throws the data in high dimension, and in high dimension, it creates linear geometry. And luckily, this root is invertible. So this is why we have something called kernel PCA. So kernel PCA, I have not put any slide for that, but kernel PCA basically is this, that if I am not able to find out linear geometry in the given stipulated data, then, and I have non-linearity also and I want to capture it, So I will use some kernel trick, throw the data in high dimension, and then apply PCA there in high dimension, which I can easily do. So this is what it has been done. Whenever my time is over, I'm not carrying watch. So whenever my time is over, you can stop.
Ma'am, you summarize it because your time was up to 2:30.
नहीं मुझे नहीं पता सर आप बताओगे तो I just go with what you will say.
10 minutes more.
So I have already explained all this. That. So this is anyway the slides are here if somebody says. So what I was trying to say is that so this is a very small example which I put on the slide to create that eigenvector and principal scopes. So this is what I was trying to say. That kernel PCA. So it is basically PCA, but it is hybridized with kernel tricks that machine learning people use. Another is PSNE, which is nowadays quite popular. PSNE also give you a visualization power into what we have. And it also helps you to capture non-linearity dependence in the data directly without using kernel. Right? So it does not involve any high dimension thinking. It does not involve that kind of mathematics which typically comes with kernel and Hilbert space mapping, etc. But it basically, from the given data itself, it creates some kind of cross covariance, and it uses KL divergence, basically entropy and divergence theorem, etc. And it tries and capture any kind of non-linearity that is there in the data. So, and moreover, somehow the method is designed in such a manner that it is very easy actually to visualize it in 2 or 3 dimensions. Its interpretability is very strong. And it is nowadays quite popular with people actually for data reduction or feature reduction. Another is factor analysis. So factor analysis is something like this, that suppose if I have 500 features with which I am working with, and I want to reduce it to, let's say, 3 features or 4 features or 5 features. So what I believe is that everything in this world, or every kind of data in this world, is governed by some virtual entity sitting on top, which I cannot see, but somehow they are the controllers. So what this factor analysis does is, it somehow creates a third layer. So I have a feature, I have responses, and on top of it, it creates a virtual layer. That virtual layer has only 3 or 4 factors, which we consider as prime principal factors, which we do not know. We do not know how to explain them. They are like Brahma, Vishnu, Mahesh, sitting somewhere on top. And we are just, going by their instruction. So we believe in this factor analysis that there are 3 or 4 important factors sitting on top, and they are controlling the entire data. So what we just do is we create a mapping here from this top layer to the bottom data layer, and we try and find out what could be this possible mapping. If I am able to establish this mapping, then I don't have to work with 500 columns. I just have to work with those 4 columns. For instance, we have students, then we have faculty or teachers, and then we have administration like principal, vice principal, or some dean or some deputy vice principal, deputy dean, etc. So if as a student, you have to say something, one way could be that you tell something to your faculty. Now, if you think that there are too many faculty and you are confused as to whom to approach to, the best thing is you go to the principal directly. So you assume that there are 3 or 4 deans and principals sitting on top layer, and even the faculty is governed by those 3 or 4 people. Whatever these 4 people will say, faculty will listen to that only. So therefore, we create that mapping, and now this faculty wala column is gone. Now it is between student and these 4 people. So therefore, we create, instead of working with n cross 500 data, what we just do is we work with n cross 4 data or n cross 5 data. But the important thing is, and this is where the whole mathematics and statistics come, that how do I create a relationship between the top layer and the feature layer? What is that relationship? If I can try and mathematically build that, then the rest of the data can be reduced. So that is what factor analysis does for us. So I think I can stop here itself. So idea basically is that there are many techniques in which the data can be reduced to a smaller size, and then you can work, instead of big data, you can work with smaller data, and when you are doing this transformation, you do not throw away the vital information that is there in the data. You try and preserve as much information as you can, and still work with the small or analyze the smaller data instead of bigger data. The conclusion will not change at all. Whatever the conclusion you have from the bigger data, the same will be there from the smaller data, because you have preserved all the important ingredient and features from the data. So that is what the whole idea is. Thank you.
Hi ma'am, for the enlightening session. Your insights into the realm of statistics and machine learning are greatly appreciated. I now invite our next distinguished speaker, Professor Anup Singh, to share his insights on the topic application of AI in medical imaging. So please.
लगा लूँगा मैं लास्ट में सबके ऊपर लिखना है. तो आधे बच्चे खड़े हो गए, आधे बच्चे खड़े हो गए पीछे. क्या करेगा तुम? टाइम ज़्यादा बच्चे नहीं रुक रहे, दूसरे डिपार्टमेंट वाले बच्चे. रिमोट आशीष कहाँ था? क्या देगा मैम का साइन हो गया और सर का. आशीष माइक ऊपर कर दो, माइक को ऊपर कर दो, आवाज़ नहीं आएगी. उनके पास माइक है ना?
Okay, good afternoon. Am I I audible last bench? जबकि last वाले सो रहे हैं लग रहा है. Okay, so I think I will start to the second part of this afternoon session. So far you heard very interesting topic about lot of type of data is there, and now principal component analysis actually is one of the very useful approach which can you can say compress the data, so you can reduce the features in a multiple way. Okay, so ma'am talk about multiple type of data and how we can call them as a features or parameters, those things. So I will provide you now a little bit different kind of data, so which most of you are familiar also. So in today's world, imaging has become integral part of our life. Am I audible last? Okay, right. So it has become integral part of our life, and I think everybody have cameras, right? So just a few questions. Where you use selfies in what are the applications you are doing with your camera? Anyone? Any camera, I mean just a phone or regular, doesn't matter which camera. What? Okay, so what are you using of this one? Selfies only or something else? Capturing the moment, okay. Saving the data, okay, very nice. What else? Any other application you have seen of this regular cameras or phone? Drones. So drones captures lot of sceneries or what else? Satellite images. Thermal imaging, okay. Medical imaging. So medical imaging you need separate one, but with the regular cameras. This side से कोई नहीं आया कुछ. रील तो बनाते हैं कुछ. Insta reels हैं. Okay. Yeah, I think so. More or less everybody is using cameras these days, right? Maybe for selfie or maybe for multiple other uses, right? Just like he mentioned that for preserving beautiful moments. So for example, this is the pictures I took 10 years back, right? So these, if this picture I have not taken, I could have totally forgotten that moment. So this picture reminded me of that moment that 10 years back I visited a place JNU, and in the canteen we were sitting and there were small copies, and this my kid was playing with that one. So it really frees that moment. If this picture was not there, I has totally lost that memory, right? So it preserves the memories, and apart from this one, so there are multiple uses, right? Some of you already pointed out also. So satellite pictures, right? We capture the pictures of multiple things that maybe geographies or your weather forecast, right? So we have uses of images in this field. Similarly, you have in agriculture, the use of imaging is growing rapidly, right? So apart from the agriculture, you have self-driving cars, right? So there for object detection you use cameras, all those things, right? So CCTV is another example that in your corridor also you might have seen the CCTVs are there, and of course these days a lot of kids also take selfies or reels or those things. Well, there are have uses and misuses, that is different, but imaging has become integral part of our life. So this is just a summary of that. What are the applications? Not only regular one, but it has use in personal life, just like preserving the memories or storing the data for a longer period, or any other purpose, just like your passport picture or other things, right? In the space, just like we have ISRO, so we have a lot of application in the space industry also. Similarly, natures, you want to see the wild sanctuary pictures, or this industry, military also, the use of imaging has rapidly grown, just like drones uses or many others, right? So in most of the part of our life, images has become very integral part, right? So these images are what you can see with your naked eyes, right? So whatever these regular image captures, it's only that information. But about inside of your body, right? If I want to take the pictures of inside of the body, this regular camera cannot, right? So we need something special type of cameras, right? But the first question arise that why we want to look inside the body, right? So there are like medical interest, clinicians are interested, patients are interested, or even as a human being we are interested what is inside our body, right? So we want to understand and characterize human body from structural point of view. What are the different body part, different organ, right? So where are these tissues or organs are located, and how are they? For example, for normal or like disease case, so how they look like. Function level. So for example, if I make a movement of my hand, which part of brain is controlling this hand movement? Right? I want to understand the functional characteristics of my body. Uh, Hemodynamic level, how the blood is flowing in our body, right? I want to visualize that, okay, blood flow, where it is more, where it is less. So if I want to have a picture of that one, so how is that possible? Similarly, physiological level, what happens if I take a drug? How it is distributed in the body? If I take the food, how it is getting digested and from that supplied to different body parts, right? So how that is possible? And similarly, molecular level also, right? So lot of times disease when happens, so any disease, so that is initiated at the molecular level, right? So it's small change in the concentration of molecule over some environment of the tissues, so disease might start. So people would like to know that what is the concentration of different molecule, right? Just like for example, you have a creatine or glutamate, some molecule. So what is the concentration of those in different body parts? So all this information particularly is required for diagnosis of disease, right? So we suffer like over the times with the different diseases. So how this information can help in disease diagnosis? After the diagnosis, treatment begins. So how the this information can also help in treatment planning as well as follow-up, right? And similarly, evaluating the response of new drugs, that we want to see that whether a drug is effective or not. If some disease is there to a person, that whether disease is getting cured over the time or not, is a particular drug is working or not. So for all these informations, we need images, okay? Particularly, so that is done by specialized cameras called. There are multiple such specialized cameras which can take the pictures of inside of human body. Okay, just like X-rays, most of you might have heard about it. Computerized tomography, CT imaging, PET, MRI, magnetic resonance imaging, ultrasound, nuclear imaging, optical imaging. So these are like some of the specialized imaging modalities which are like routinely used in the hospitals, particularly. You can see that some of these are available in small hospital, but in the multi-specialty big hospital, all of these will be available, and they have various applications. So this is just like examples of ultrasound image that is widely used for monitoring the growth of a fetus. This is X-rays, particularly for if you some bones are fractured, so to get the picture of that one. Similarly, CT imaging for if somebody has stroke or hemorrhage. So usually it is preferred also. Similarly, images of inside a body can also be obtained if you have a tissue. As such, we don't call it a medical imaging, because you are taking the tissue out and then studying under the microscope, and then you're taking high resolution picture. I mean, using the this high resolution camera. So all these pictures, just like that, is the MRI image of almost the whole body. So these imaging modalities, just like ultrasound, it's not only the abdomen. You can do it the other body part also. Similarly, MRI, so you can acquire the images of brain, over leg, over abdomen also. Similarly, CT imaging also. So these are like different cameras which can be used to image information of inside our body. Okay, so now let's shift to the understanding of the image. Okay, so the most of the images, whether we capture with a phone or those things, these days we are having the digital images. Okay, so digital image, what do you mean by digital image? Anybody? So have you seen your picture and try to zoom it? What happens if you zoom it too much? Pixelated, right? So it start pixelated. So for example, I take a very smaller passport size picture and start zooming, right? So it become pixelated. Now, as ma'am mentioned already, so the data you can put it in the form of matrix, right? So if you want to actually see that whether this picture is a matrix or not, so you see you note on these gray levels and find the what is the value. Okay, so if you see or read this image, so apparently it is actually your data matrix, right? So for example, this is the gray image of with the regular camera. Its intensities are distributed between 0 to 255, and if you read using some of the software like a MATLAB or Python, so you will see a matrix. So that matrix will have the entries between 0 to 255 something. Okay, so apparently your images, any image you have, that is just like your matrix. Okay, so you can define using this one, and once you have matrix, you can do all kind of operation. You find your eigenvalue, eigenvectors, or other you do the transformations also. So these are some of the operations. Okay, so this is just like a previous was with the regular camera. This is with the MRI. So MRI image of a human brain in societal orientation. So same way, if I want to see that as a form of matrix, I can put a matrix grid. So these small are voxels are called pixels, right? So these are the element, we call them pixels. This is the smallest unit of image. Okay, so there are some informations related to image also. Field of view. What is field of view? If you take a picture, what is the field of view? So it is the maximum scene you can have physically. For example, if I am taking the picture of this one, so I can have seen only this room. Okay, so over if you have a close-up of somebody, so that you can have only his face. So it is like a geometric dimensions you can capture. So your field of view for self is different, for scenery it is different, right? So that is your field of view. Then you have acquisition matrix, mean how many pixels you can put in that field of view, right? You have, for example, 8 megapixel camera or 20 megapixel camera. These days the phone comes with the growing megapixel. So what is megapixel? This is just a resolution, right? So that given a field of view, how many pixels you can put there, right? 8 megapixel means 8 like million pixels you are putting there. So this is the normal pictures, and you have the pixel size actually, that whether it is a 1 millimeter size or it is a one less than that or bigger than that, right? So these are like some of the information you require related to images. Okay, so you can also, when I display image, if I put a pixel or my cursor somewhere in the image, I see some value, right? So that value is called intensity value at location ij. So this intensity apparently for regular images, what is it? We can relate it with that it is a reflection of light, right? If you have a picture, so if your intensity picture you are looking at nose or any characteristics, so it is simply reflection of light. In MRI it is different. In CT this intensity is different. Okay, so this is just like one way to define images through the matrix. Another you can define it with the help of a two-dimensional function also. So it is a function from not two-dimensional, but it is function from grid I by I to R, mean set of non-zero this integer to the real numbers. So that is another definition of this image. Okay. So another important difference is image when you read in the software just like, okay, so regular Cartesian coordinate system start from the 0 0 this side. In the when you are reading in a software, like your programming environment like MATLAB or C or C++, so your zero start from the top corner. So your first pixel is actually there. So we call it like 1 1, right? So similarly, you can have here 10 rows are there, so you can have 1 10 or like this one. Okay, so that is your image. So now we have covered about what is the image, what is the digital image, and how we can define it with the help of your matrix or in the form of the function. Okay, so now we will go to the next topic, that is called processing. So what do you mean by processing? So if you take a selfie or pictures, what do you do with that? Editing. What do you do in editing? Rotation, apply filters, right? You might have heard about apply some filter. So filter, what they do? They change the contrast, right? Brightness, composite. So these days in your phone itself there are so many these type of filters which our image processing tools which you routinely or each day are using, right? So given this image, I can have same picture, I can do lot of operation. For example, if I change the brightness contrast, I get this picture. If I do some further normalization called histogram equalizations, so I highlighted the fine details which were dark here and nicely visualized. Similarly, if I compute the gradient of image, just like derivative, right? So you might have studied about derivative. If I compute the derivative of the image, right? It's a function, so I can compute the derivative also. So it highlights the edges or fine details, right? Similarly, I can do the sharpening of the images, or I want to detect or annotate a particular region. So I can just like in the brain, I annotated a region called corpus callosum. Okay, so where I want to know that what is the volume of it, what is the area of this region. So we can also draw the different region of interest. Okay, so there are various tasks which we do and we don't realize whatever we are doing this one. So there are tools or there are algorithms behind that. Okay, so those algorithms actually that's what become part of the image processing. So in image processing, when we talk about it, is all about image enhancement, image noise reduction, right? So all the data or images which you get, it has a noise inbuilt in. Okay, so our task is to reduce the noise so that when you apply the filter, it becomes more smoother. So same thing is there are sometimes some artifacts can come in the image. So reduction of the artifacts or sharpening, we want to make it more clear the pictures. So over segmentation, we want to mark a particular region. Over, for example, in a disease state, someone has a tumor or cancer. The doctor want to know, mark its boundary, what is the size of tumor, right? So that is part of the segmentation. Similarly, classification. So you want to classify whether a person image is normal or disease. Mean person that image has some abnormality or not. Okay. Over whether the disease is low grade or high grade. So there are multiple classifications challenges also. So and object detection, image fusion. You want to fuse information from two different things. So all this is like part of image processing. Okay. So next I will just focus on, as I mentioned, there are multiple imaging modality. So we'll focus on only on the MRI because that is what mainly I use. So MRI, anybody have seen or know about it?
Seen.
So what is it?
उसके अंदर जाना होता है फॉर इमेजिंग और काफी देर तक स्टिल रहना होता है, मूव करेंगे तो फिर दोबारा से
Then and did it make some noise?
Heavy noise.
So MRI is like a special machine which when you go inside there are always noise tuck 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 over there. There are even during the image acquisition there are multiple type of sounds keep on coming. Okay, so those are like the part of that one, and usually you have to lie down depending on the case 20 minutes, 30 minutes or 1 hour also. Okay, depending on how much information doctors want to accept. So this is like quite common. So normally it is a MRI is a, as the name implies, a magnetic resonance imaging. It's a special camera based on the magnet, but it's most of the scanners or this MR instrument which we have, these are not a regular camera, just this magnet which we used to play during our childhood. So these are superconducting based or electromagnets. Okay, so these are like if you see, they are consist of multiple components. So there are like main magnet, that is your superconducting magnets, and there are gradient coil, radio frequency coils, and other component also. Okay, so I will not go into much detail, but each one of them has a particular task. Main magnet generates the magnetizations in our body. Okay, so as such, normally the main signal which we get in the magnet, just like in the regular pictures, right? It is just a reflection of the light. Here it is the proton present in our body. So our body have a lot of protons. Where?
In the nucleus.
Blood, okay.
I think everywhere we are made up of atoms.
Yes, we are made of atoms, so there are a lot of protons, but which is the most important molecule which has the protons, and that is present in abundance in our body?
Carbon.
Water, right? So our body is made up of around 70% water, H2O. So there are so many protons in our body. Proton is a charged particle, right? And it also has spin. So each proton, if you look, it is a tiny magnet. So in our body there are billions or trillions of the tiny magnets sitting, but still we are not a magnet, right? Because their magnetic properties are in random directions, so they cancel out. So we are almost diamagnetic basically, our body. So we cannot pull, just like we put a hand over in front of metals, we cannot like pull it, right? However, the moment you place a person inside the body, there is a magnet. Okay, so this magnet try to orient these protons parallelly or anti-parallelly. Mean their magnetic field try to orient. Okay, and because of that, there is a tiny difference or tiny magnetic field is built in our body. Okay, that is called magnetizations, that purpose. Okay, and that is detected using radio frequency coils, which are separate one, and also localized using gradient coil. So this picture actually summarizes how from the protons present in our body to the final picture. Okay, so we that happens. So when we place the person or object in a body, okay, so in this magnetization which we have through the large magnet, we try to create the magnetization of the body, and that we then use RF pulses to send in the transverse plane, or you can say low energy to high energy state, and that signal we try to detect using the RF coils. So apparently when we remove the V1, so this start decaying again. So when magnetic field start changing, so changing magnetic field induce current according to Faraday's law. So that is what we detect as a signal, and if we take the Fourier transform of the signal, okay, so I'm not sure how many of you have heard about the Fourier transform. So we can get spectrum, but if we apply the gradients, the gradient do the encoding, okay, so and then the data which we get, that is called K-space data actually. So you might have studied about this Fourier in your class. If not, then you might study in the next semester. So usually we get Fourier space data. This is called K-space data. And if we take inverse Fourier transform, so that's what you construct. Okay, so this is just like a picture that we get. So apparently from MRI we can get high resolutions pictures of body. Just like this is the brain, 3D data of the brain, 3-dimensional data. So very high resolution picture we can get of brain, not only brain but other body also. So same data you can do image processing and do the rendering, so create a 3D structures, and one can even see or play with it the way you want, and it's very helpful for surgical planning, or you can have 3D model also you can print. So we can have MRI not only brain, but we can have any of the body parts. So just like your brain, your abdomen, knee, calf, or heart, breast, your spine, even whole body. So you can have the MRI images of any body parts, and in any orientations like sagittal, coronal, axials. Okay, so normally these are the three planes we use, and yes, so it provides a high resolution pictures of inside of the body, and these pictures are used for detection of diseases. Just like this person has some abnormality here, right? So that was marked in this region of interest RY. Okay, so that is how these images are useful, and with MRI we don't get only single type of picture. Just like with your camera, you are getting only single type of picture just based on the reflection of light. With MRI we can get multiple type of information. Okay, we can have structural information of the body, we can have diffusion weighted images, very high resolution structure information also. We can have perfusion, like what is the blood flow, blood volume information. We can have functional activity, that which part of the brain is responsible for blinking of eyes, or emotions, or like your hand movement or finger tapping. Similarly, molecular information we can have. So same magnet can be used to get a different type of information, and so normally from the scanner we get these images. These are called structural images or weighted images, but and these are like grayscale images mostly we get, and we can do some post processing or analysis to create more meaningful information. Just like this is the showing a functional MRI map computed from the this fMRI data. So that is telling that some region of brain is localizing a particular activity. Similarly, we can have our brain white matter tracks are there, particularly the how this is how our brain is structurally connected, right? So our brain is functionally connected and structurally. So so these fibers we can visualize. These are very fine fibers. So we can see that how well they are connections, and in lot of particularly there are some diseases like related to demyelination, where these fibers get like distorted, so leads to a lot of problems. Okay, so similarly molecular information, for example, glutamate is one of the molecules that is called neurotransmitters, so we can have its pictures also using the MRI. So there are like multiple information we can extract from the same camera, but using different techniques in it, that is called pulse sequences. And that's what I think if anybody have lie down in the magnet, so there are different pulses that are given during the scannings, and you get a different kind of images. Okay, so this is just like example. For a brain, for a single slice, you have multiple type of data. So huge amount of data we get from the like MR scanners, and this data is usually used by the clinician called a radiologist for detecting the diseases, or planning the treatment and other purpose. But lot of information can be extracted after doing processing of this one by using some mathematical formulations. Just like there are some of the mathematical formula which we use to further analyze it and create a new type of images from this one. So these are like called quantitative maps. So these are related to physiology in some ways. Some are just like relaxation maps of the body, or these are the blood flow, blood volume, how much blood flow is in a particular region. So that to get this information, you need to do some mathematical modeling of the data which you get. Okay, so that is how it happens. So these are the images of one patient having a brain tumor. So now shall we continue, or like what is the? Shall we continue, or yes? Okay. So now after having what is the imaging, medical imaging, and we talk about digital image processing and some information of the what is MRI and what it can do. Okay, now let's take a look of one kind of disease that is called brain tumor. Okay, so brain tumor, anyone, what is brain tumor? Anybody heard about it?
सुना तो है.
extraordinary growth of cells. Yes.
The dead cells accumulate in one.
Dead cells.
Maybe they accumulate in.
Yes, so these are not dead cells, these are like very aggressive cells. They try to make the or brain cell, they can die over the time. But mostly these are like uncontrolled growth. So these are the part of the body, but some cells becomes like uncontrolled because of some reason. There is some kind of genomic level mutation happens. Till today, nobody understands fully why this happens. Okay, what is the exact reason nobody knows, but yes, people try to make a different reason behind this one. That okay, because of this or that one. So apparently, it is the cells that can malfunctions. Their structure can become a little bit different, or there is a tendency that any cells which is there it will die after some time, but that death might prolong. So their number growth is more, or like they might die a little longer times. So all this is like form a disease called like a cancer, or brain tumor is also part of that one. So in brain tumors, when a disease happens, so the natural question clinicians would like to know, detect and localize where it is there. Okay, so once this is detected, then next question start classification, right? So if there is some abnormality, so abnormality may be tumor or non-tumor. Okay, they may look similar. Similarly, if there is a tumor, then what is type? Is it like benign or malignant? If somebody has benign tumor, it's still okay that a person can live longer. But if it's a malignant tumor, then it needs to be treated very carefully, and persons even after treatment may not survive longer. Okay, so one need to know that what is all these types, and also treatment planning, that where to do the surgery, then after the surgery radiation planning is there, where and how much radiation need to be planned. So all this is a part of the questions that are required to be answered by the clinicians or radiologists. Okay, and for all this, I will just skip this one. So normally for getting answers, we do a neurological exam, and then medical imaging is prescribed to localize or study, and biopsy samples are taken, and further examination happens to actually finally characterize what is the disease and how to proceed further. And here medical imaging is playing a key role in answering a lot of questions, particularly for detections, classification, tumor gradings, as well as treatment planning. Okay, so this is this imaging is very helpful and is routinely being used in most of the hospitals. So imaging is there, we can extract the information, but there are still a lot of challenges. Okay, so just like a time, long data equations. So data equations, because when there is a patient, so patient get impatient, right? So they want that, okay, I should not be waiting for long, because person is in a different state of mind. So data acquisition times are longer. How we can reduce delays in data analysis over reporting over treatments. So sometimes a patient has to wait for 2 days or 1 week, or in case of certain scenario it may be more than a week. And depending on the disease, these are very aggressive. Sometimes in 1 week they might get in the next stage also. So, and next is the quality of data. The data which we are getting that also suffer from a lot of issues or challenges. There may be noise, artifact. Sometimes the data might get from transferring from one place to another one, or a technician forget to acquire a particular sequence, right? So there are inconsistency and variability. One hospital may be acquiring different type, another may be different type, right? So there is no standard still today also, and there is a subjectivity or user wise. For example, there are 2 radiologists. You went there, and both have different experience or different expertise, so their reporting can vary also, right? So all this information, there are the challenges in healthcare domain or medical imaging domain. So people has been, or researcher has been working to address these one, and recently artificial intelligence has been playing a key role in addressing these ones. Okay, so it's so artificial intelligence is just like data-driven models which are used to solve these problems. So I will not go into much depth. but it is like there are like conventional machine learning based approaches which where you need to give the different features, just like ma'am already mentioned about you have to extract the feature from the images, and then you try to develop these models. That may be simple logistic regression or advanced neural network models, but there are alternative deep learning or convolution this network based models, so which automatically can extract the information by using a different kind of convolution operations. Okay, so convolution is a mathematical operation which you will learn soon. It is like a very useful operation, so where you can extract the information automatically. So this is in type in the form of kernels actually. We use a different kernels called convolution kernels, and it try to learn automatically different features or information, just like in an image when you try to identify persons, how you can do. So apparently you will look the eyes or ears or some pictures features of that one, right? So these convolution kernel also try to see like vertical edges, horizontal edges, or some other type of patterns, and try to combine these patterns in the deeper layers of the models, so that you formulate actually entire pictures, and finally solve the problem, just like it's a classification problem or segmentation problem. Okay, so that's how some of these
Convolution and neural network
deep learning
recurrent
networks are there. So
long
convolution
short
neural
term
network,
memory.
that's what I was mentioning, and there are
Long short
many advanced version of this one. So I will not go into depth because that
generative
requires more time.
associated networks.
So just like this one, so there are two images here. Okay, so one is a patient having low grade tumor, and another is a patient having a high grade tumor. So how a doctor approach particular radiologist? So they will examine the images and look into the like some patterns that these two have different. For example, in the right side, doctor see that there is a more bright spot, right? And this has less. So based on that, try to formulate, but it is not one image they see and get the decision. They might have seen hundreds or thousands of patients and try to learn the information. Okay, high grade usually show this type of information, and low grade show this type of information. So the same way, the machine learning or the deep learning model which we build, we train them with a large amount of data, and they try to learn the features either through the person who is trying to build this model, or through automatically based on deep learning. So apparently it is the features that need to be appropriate features need to be identified and used for differentiation of these ones. Okay, so this differentiation comes under classification of two diseases, just like low grade versus high grade. There are like benign versus malignant, so many such scenarios. Okay, so I will just show some of the activity which we have been doing in IIT. So one of the problem which we are working from last few years is the brain tumor. So here we get the images and then do the annotation called the brain extraction. So and then after brain extraction we try to further segment the brain into normal versus the abnormal. In the abnormal also there are sub-component of that, just like tumor don't is not a one structure, it itself have multiple components. Just like there are some dead cells, there are very aggressive cell over called enhancing tumor over like necrotic components. So it need to be like properly marked. So we are like developing method for automatically labeling these regions. Similarly, for analyzing the data, just like mathematical modeling of the time series data which we get from here. So there also with the conventional nonlinear least square method as well as advanced deep learning approaches, we try to see that how we can reduce the effect of noise or how we can speed up this analysis. And finally, using this information for grading or classification and also radiation planning. So recently we started that how we can plan the radiation, automatically generate the contours, particularly called gross tumor volumes or CTV, PTV. So they are useful during the radiation planning, because the person who have the tumors after the surgery, still they need to go through the radiation cycle, and radiations mean we use very high intensity X-rays. So these should be planned in a proper way so that the functional over normal cells get a minimal impact. So if you give them like a more accurate marking of this one, so patient will have less radiation toxicity. Okay, so these are like some of the work which we have been doing, and this is just like annotation work where we develop a deep learning based model for automatically labeling of the brain tumor. Not only brain tumor, but it can work on any kind of image of the brain. That can be stroke, like tumor over normal. So we tested this algorithm on multiple type of data, and this can provide the entire annotation within a few seconds. So that was like a quite rapid approach. Similarly, this is another model we developed for automatically segmentations, and this I already mentioned. So here we are speeding up the mathematical modeling process using the deep learning approach. So these are some of the work I will, I think, skip because of the time constraint. So all related to the brain tumors, there are multiple examples where we have to do different classifications, just like a low versus high grade. This is just like one of the called PA versus glioblastoma. Glioblastoma is a very aggressive high grade, grade 4 brain tumor, and palliative stroma is like usually it was classified as a low grade. But both on the images look very similar, and it was very difficult for the doctors to classify that whether it's a low or high. In case of low, persons can live very longer, and treatment can be like in a different way. But in the high grade, it has to be like GBM patients survive only with a median lifespan of 15 months only. So yeah, few can survive for 3-4 years also if proper treatment is done. But mostly median age is like 15 months. So that is like developed some methods for automatically classifications of this one. So similarly, this is the work which I skip. So this I will keep in the slides if somebody want to go through. So okay, so based on that we developed then a software solution that can automatically analyze the data of the brain tumor patients, and we have deployed in a couple of hospitals now, and it's also being used for like regular diagnosis purpose. So not directly, but it is assisting the radiologist in making the decision rapid and more objective decision. Okay, so if somebody want to play with the images, there is like some online data also called public data repository. It's called BRAX, Brain Tumor Segmentation Challenge. So a lot of data of the MRI images are available on this, like one can get from this public data, and want to work, they can use it. So we have used this also. So most of the data which I presented before, it is from the local hospital we have obtained. That is from the Fortis or AIMS, really. But this data which I mentioned, this is called BRAX data. It's a large data set of more than 2,000 patients. So this is like one of the challenge we participated in 2021, where we obtained certain accuracy. This year again we participated. So this time on the conference was being held in the South Korea. So on a different challenge. So I think yesterday itself one of my students was presenting, and he got the first award in this one. So that was a long journey. And another work was also brain tumor, but is a different category. So another student got the second prize. So that was like the long journey we have traveled from a couple of years. So this is like an international conference which was very competitive, and we were able to get like a quite good work here. Yeah, so with this I will summarize the talk. So imaging is a rapidly growing field, not only medical imaging, but all the aspect of life we are finding its applications, and particularly medical imaging also. So there is a lot of scope of the job also, or like a research topic or a project you want to do. So there is a lot of scope in this field. There are a lot of challenges in image processing, which I already mentioned, that are related to artifacts, noise, or like classification problems, segmentation, annotations. So these are some of the problems, and AI has a lot of potential to address those problems more efficiently. And still, I think a lot of things has to be explored. And last but most important, ethics and regulations are important. When you use the images, so data privacy, data protection over anonymizations should be done. For example, you go to the image of patients, it need to be anonymized. Main patient identity should be hidden, so name should not be disclosed. So there is like anonymization that is usually done. But if by mistake you get a data that is not anonymized, make sure to anonymize that one. And similarly, consent from the patient or persons that whether I can use it, right? So these days, like even we are taking the selfies in the public, going everywhere without asking them and sharing it everywhere, it is not right. And very soon you will see that a lot of regulation will come, and particularly from the patient point of view. So it is very important that the data which we get on this one, before sharing, we have to be like very careful. Okay, yeah. So use AI because it is a very novel or like great technology, but avoid its misuse. Okay, so with this I will end this talk, and any questions?
Not a question, but a guidance. Like I have a project. I have
Say loudly.
and we are getting a project on behalf, like we have named it. We need a realization centers online project. We have realization very abundance, not of for a reason they are more. So what we are doing is there is ML model called Postnet. We are using that. So for that, we capture a patient real time data that will pinpoint the joints. Patient will perform a specific type of exercise, and how like it will generate a report like how it's accurately doing that exercise. It will like that report will go to a different system of the sign it and make a
एक्सरसाइज का तो नहीं पूछ रहा अपना
what
प्रॉब्लम
we are studying,
ये कर नहीं रहे हैं बट
what
पूछ
our
रहा
report is generating for like how can we make it more identical and more
Yes, so when you talk about authentic report, you have to involve the clinician there. And because so far, they are the persons who will say that whether it is right or not. So one way is that if you have the regular way and already such reports are available, you can use them as a control and but compare your. If not, you need to involve the persons who can validate that. Otherwise, you may use some symmetric to tell that okay, I get this much accuracy, this much accuracy. That's okay. That is from the like computation point of view. But clinically, whether that makes sense or not, so it has to be validated by the clinician.
like what from our end what we can provide more like more people who are
हेलो कहाँ हो
Yeah, so one is the qualitative
अभी तो चल ही रहा है
visualization of result which you have. Another is the metrics. There are different metrics which you can
क्या चीज़
report and try to explain to the doctor that
हाँ
okay,
हाँ
this
करवा
is
लिया
the
था
result. And the trust will be built between.
खाया था
Yeah, so
थोड़ा
I
सा
think more
खाया था ना थोड़ा
specific, I mean, need to look that one and then we can
आके बता दूँगा
yes.
ठीक है
Any other question?
ठीक है रख रहा हूँ मैं ठीक है
Okay.
Sir, what is probability that benign may convert in cancers?
Probability is less, but there is yeah. So normally
What should be the precaution?
yes, so usually for particularly for the brain tumors, benign is there. It should be better get surgery removed. So one can do the surgery. After surgery, you don't need to do the radiation or other things. So as such, a lot of people leave it and just follow. So maybe for after 5 years, 10 years, 15 years, there is chance that it can convert. So it is the most of the time people do prefer for leaving it. But if that benign tumor is pressing other body part, you may getting very frequent headache or some other your functionality is affected. Then surgery is done and they remove that one. In that case, symptom will be relieved. So yeah, so rest it is a yeah. So there are chances. Some type of benigns might convert less chance. Yeah, there are chances. Even low grade can convert into the high grade. So there are, I think, in brain tumor itself there are more than 200 types, and some are like slow growing, some are fast one. There are and similarly other type of cancer. So it's a very challenging issue. Okay, thank you for the attention.
थैंक यू सर
आप आ जाइएगा
Thank you, sir, for sharing your valuable insights with us today. Your perspective on the applications of AI with medical imaging have given us a lot to think and learn from. Now, every successful session is a result of collective efforts and guidance. May I request Dr. Lokesh Kumar Srivastava, sir, to please come forward and present the vote of thanks for today's session.
फोटो निकाल लेना है ना, जियो टैग वाला निकालना।
Sir, Professor Aparna Madam, distinguished speakers of today's workshop, our respected Principal Sir, Vice Principal Ma'am, esteemed faculty members and dear students. As we come to close of this insightful workshop on machine learning for inclusive development, shaping India's future, I feel truly honored to extend our heartfelt gratitude to everyone who contributed to making this event a grand success. First and foremost, we express our sincere thanks to our esteemed guest, Professor Aparna Mehra Madam, whose erudite insights enriched our understanding of dynamic field of machine learning. Ma'am, your expert lecture on statistical ideas in basics of machine learning was both inspiring and enlightening. You simplified concepts such as regression, PCA, and factor models for feature selection while still providing deep mathematical and statistical perspectives. Your ability to keep the mathematics simple yet meaningful made the session both accessible and impactful. Thank you. Thank you very much. We are equally grateful to Professor Anup Singh sir, whose lecture on application of AI in medical imaging shed light on the foundational concepts and transformative potential of artificial intelligence in healthcare. Sir, by highlighting the use of machine learning for disease prediction, your demonstration how these innovations can serve society, the nation, and humanity at large, taking us closer to the realization of the dream of Viksit Bharat. Your way of sharing knowledge with clarity and depth is truly commendable. Our heartfelt thanks also go to respected Principal Sir and Vice Principal Ma'am, DBT Star College Coordinator, for their constant encouragement, guidance, and support. We sincerely acknowledge the tireless effort of DBT Star College Department Convener and organizing team convener, Mr. Manvendra Yadav, along with Ms. Manisha Chauhan, Dr. Shalini Agarwal, Mr. Mahesh Kumar, teacher in charge, Professor B.S. Dixit sir, senior most faculty, and all our dear faculty colleagues. Your meticulous planning, hard work, and dedication ensured the smooth execution of this workshop, making it memorable academic experience for all. Last but not least, a special thanks to all the participants whose enthusiastic involvement, thought-provoking questions, eagerness to learn turned this workshop into a truly engaging and enriching platform. As we conclude the day one session, we carry with us valuable knowledge and inspiration that will guide us towards a new horizon in machine learning, artificial intelligence, and quantum computing technology that holds immense promise for inclusive development. This workshop has strengthened our understanding of how these tools can address real-world challenges, foster equity, and drive sustainable growth.